The deep Pacific's abyssal plains are a world of darkness, stretching for thousands of miles beneath the waves. Here, sunlight never penetrates, and the only illumination comes from the faint glow of submersibles, and the occasional bioluminescent creature drifting by. The pressure is immense, enough to crush unprotected equipment, and for decades scientists believed this realm was stable, unchanging and almost lifeless, a silent desert at the bottom of the sea. Yet, even in this extreme environment, life persists. Creatures here survive on the slow, steady rain of organic matter, tiny particles of dead plants and animals drifting down from the sunlit world above, known as marine snow. Ancient invisible currents carry precious oxygen through the water, maintaining a delicate balance that supports a surprising diversity of life, from microscopic bacteria to strange, otherworldly animals. One of the most intriguing regions is the Clarion-Clipperton zone, a vast, remote stretch of seafloor that has recently become a focal point for both scientific exploration and commercial interest, especially as companies eye its mineral wealth. In this isolated expanse, researchers have made a discovery that could upend our understanding of life itself. Evidence that oxygen is being produced in total darkness without the help of sunlight or living organisms, a process previously thought impossible. This phenomenon, now called dark oxygen, is challenging long-held beliefs about the chemistry and biology of the deep ocean, and forcing scientists to reconsider what is possible in one of Earth's largest, least explored habitats. The source of this mysterious oxygen? Strange, potato-sized polymetallic nodules scattered across the seafloor. These nodules, rich in valuable metals, are also at the center of a growing debate over deep-sea mining and its potential impacts. As mining companies prepare to extract these resources, scientists are racing to understand the full implications of this discovery. The stakes are enormous, not just for science but for the fragile ecosystems that could be disrupted forever. The abyssal plains, once dismissed as barren wastelands, are now revealing themselves as dynamic, mysterious, and vital to the health of our planet, reminding us how much we still have to learn about the hidden depths of Earth's oceans. The first clue appeared in 2013 almost by accident during a routine deep-sea research mission. Andrew Sweetman's team was investigating the mysterious Clarion-Clipperton zone, a vast stretch of the Pacific Ocean floor known for its mineral-rich nodules and extreme depths. Using specially designed sealed chambers, they set out to measure how much oxygen was consumed by the creatures living in the mud, expecting to see oxygen levels steadily drop as animals and microbes respired in the darkness. But to their astonishment, some chambers showed a puzzling increase in oxygen, as if the seafloor itself was somehow generating it. At first, the team suspected faulty sensors, a common frustration in the challenging high-pressure environment of the deep sea, where equipment often malfunctions. But the anomaly kept appearing, and it was most pronounced over fields of polymetallic nodules, those strange metallic lumps scattered across the abyssal plain. By 2021, after years of repeated experiments, new high-tech equipment and rigorous controls, the team confirmed the effect. Oxygen was indeed rising inside sealed chambers placed on nodule-rich seafloor, defying all expectations. They painstakingly ruled out every possible error, leaks in the chambers, contamination, even the presence of photosynthetic microbes that might have snuck in. The only explanation left was radical and unsettling. Something non-biological, right there on the seafloor, was producing oxygen in total darkness, without sunlight or life. This finding upended everything scientists thought they knew about the origins of oxygen in the ocean, challenging decades of established theory. The mystery only deepened, demanding a bold new look at the hidden chemistry of the abyss, and raising questions that no one had ever thought to ask before. With biology ruled out, attention turned to the polymetallic nodules themselves. These metal-rich rocks scattered across the seafloor are not inert. They're chemically active. Scientists proposed the geobattery hypothesis. Nodules generate a small electric field, with the top exposed to oxygen-rich water and the bottom buried in low-oxygen sediment. This voltage, measured at up to 0.95 volts per nodule, could trigger electrolysis, splitting water into hydrogen and oxygen. While a single nodule's voltage is low, clusters might combine their energy, producing enough oxygen to explain the chamber results. Even when all biological activity was halted, oxygen production continued in the presence of nodules. The geobattery idea recasts these rocks as silent electrochemical engines, generating oxygen in the deep, dark ocean for millions of years. A new, abiotic pathway for oxygen production had been hiding in plain sight. The discovery of dark oxygen upends a century-old belief, one that held that nearly all free oxygen on Earth comes from photosynthesis, powered by sunlight. For generations, scientists thought that without light, oxygen production simply wasn't possible. But now, evidence from the deep ocean is rewriting that story, revealing a hidden world where oxygen can be created in total darkness. If nodules can generate oxygen through electrolysis, the deep sea is not just a consumer, but also a source of oxygen. This means that even in the absence of sunlight, chemical reactions on the ocean floor can split water molecules, releasing oxygen into the surrounding water. It's a process that could be quietly fueling life in places we never expected. While the global impact may be small, locally this process could be vital, reshaping our models of ocean chemistry and life-supporting cycles. In certain regions, these oxygen hotspots might sustain unique ecosystems, providing a lifeline for organisms adapted to the deep's extreme conditions. The deep ocean, Earth's largest biome, is far less understood than we thought. Its vastness hides countless mysteries, and every new discovery challenges our assumptions about what's possible in the absence of sunlight. Unique conditions, pressure, cold, and mineral composition, enable geochemical processes we never imagined. These environments foster reactions that can create energy and resources for life, even in the most inhospitable places. This finding forces us to rethink the interplay between geology and biology. The boundaries between living and non-living systems blur as rocks and minerals become active participants in sustaining life. Rocks on the seafloor aren't just passive, they can actively shape the chemical environment for life. Microbes and minerals interact in complex ways, creating microhabitats and driving cycles that support entire communities. The paradigm shift opens new research frontiers and challenges our assumptions about how life and Earth systems interact. Scientists are now racing to explore these uncharted territories, searching for more evidence of dark oxygen and its role in the deep sea. The deep sea is a dynamic, creative frontier, still full of surprises. Each expedition uncovers new forms of life and unexpected processes, reminding us how much remains to be discovered. Our understanding of the planet's most mysterious realm is only beginning. As we continue to probe the darkness, we may find that the deep ocean holds the keys to life's resilience and to secrets that could change our view of Earth forever. A non-biological oxygen source could reshape our understanding of life's origins. Before photosynthesis, early Earth was oxygen poor, yet if nodules or similar rocks produced oxygen, they could have created oases for microbes to adapt to aerobic life. This gradual transition may explain how life evolved to use oxygen, bridging the gap between anaerobic and aerobic worlds. The implications reach beyond Earth. Oxygen is often seen as a sign of life on other planets. But dark oxygen shows that geology alone can create oxygen, complicating the search for extraterrestrial life. Future missions to moons like Europa or Enceladus must be cautious. Oxygen might not always mean biology. Still, the geobattery hypothesis expands the possibilities for habitable worlds, suggesting rock-water interactions could support life anywhere. The interplay of geology and chemistry may be a universal recipe for life. If nodules produce oxygen, they may be a lifeline for deep-sea creatures. The Clarion-Clipperton zone hosts unique species, many living directly on the nodules. A steady trickle of oxygen could make these rocks biological hotspots in an otherwise oxygen-starved world. This may explain the rich biodiversity found on nodules, from sponges to corals. Deep-sea mining threatens to strip away not just habitat, but a vital chemical process. Past mining simulations have left barren scars that haven't recovered in decades. Removing nodules could extinguish a fragile web of life with consequences we barely understand. The stakes for conservation and policy are higher than ever. Not everyone is convinced by the dark oxygen hypothesis. Mining companies and some scientists question whether the observed oxygen is an artifact of the experimental setup. Critics argue that any oxygen produced might dissipate instantly in the open ocean, making little ecological difference. The debate is fierce, with industry interests and environmental concerns colliding. Andrew Sweetman's team stands by their data, pointing to repeated results across multiple expeditions and equipment. The burden of proof now lies with researchers to show the process happens naturally, outside sealed chambers. The controversy highlights the challenge of proving radical new ideas in science, especially when the stakes are so high. The next step is clear. Scientists must prove dark oxygen production happens naturally on the open seafloor. Detecting hydrogen alongside oxygen would be the smoking gun for electrolysis. New sensors and long-term observatories are being developed to monitor these gases around nodules. Researchers will map where and how much oxygen is produced and link it to the health of deep-sea communities. The goal is to integrate this knowledge into our models before mining decisions are made. Only with rigorous independent science can we understand the true role of nodules in the deep ocean. The future of one of Earth's last frontiers depends on what we discover next. The dark oxygen discovery arrives at a pivotal moment, as the world debates deep-sea mining. Polymetallic nodules are at the heart of a potential multi-trillion-dollar industry, and a fragile ecosystem. Environmental groups in many nations are calling for a moratorium, arguing we know too little to risk irreversible harm. If nodules are a life support system, their removal could trigger cascading effects we can't predict. Mining companies argue their metals are essential for green technology, but the loss of a unique geochemical process complicates the equation. The real question: can we justify destroying a mysterious, life-sustaining ecosystem for our own gain? The answer is far from simple, and the decisions made now will echo for millennia. The faint glimmer of oxygen in the abyss is a reminder of how much we have yet to learn, and what we stand to lose.